All right, 13.1, moving into the last chapter. So we'll do 13.1 and 13.2, although there is more in this chapter in the textbook. That's all we're going to cover in this course, is just the first two sections of chapter 13. And the entire chapter is about ANOVA, but the first two sections are about one-way ANOVA tests. And these are tests that are used to compare multiple means to one another, and they're very, very similar to the homogeneity of proportions test that we did in 12.2. Only this will be for means instead of proportions. Okay, so with ANOVA testing, oh, by the way, ANOVA is short for analysis of variance. And we'll talk a little bit about why we do an analysis of variance in order to determine if the means are the same or different. But for now, let's just say with ANOVA testing, the null and alternative hypotheses are always the same, right? They're always, the null hypothesis is always that mu1 equals mu2 and so forth, all the way up to mu k, right, for however many means you're testing. And then the alternative is that at least one mean is different from the others. Okay. So two things that you might think about this. Number one is, why don't we just compare the means, compare two means in pairs using the techniques from 11.2 and 11.3? In other words, if I want to compare four means to each other, why don't I just compare mu1 to mu2 and mu3 to mu4 and whatever, right? But so we'll answer that question. And then the second question is, why are we doing an analysis of variance when what we're really trying to compare are the means? So to answer the first question, note that the more tests you run, the more you increase the probability of making a wrong decision. And I'll let you read your textbook for more information there if you're interested. But you know, the errors compound, right? So the more tests you run, the more likely you are to make a wrong decision. And the other thing is that, to answer question one, is that would require a lot of tests, right? If you were comparing four means, for example, you'd have to run 6 tests. You'd have to compare mu1 to mu2, mu1 to mu3, mu1 to mu4, mu2 to mu3, mu2 to mu4, and then mu3 to mu4, right? Whereas with an ANOVA test, you can just do it all at once in a single test. So that's to answer the first question. Now to answer the second question. Your book has some pretty good visualization of this, okay? Which I can't remember if I printed out. No, I didn't print off the visualization, but you can look it up in your textbook if you're interested. But basically, the reason that we're comparing variances, the variances that we're comparing are, we're comparing the within sample variances of each individual sample to the overall variability between the samples, okay? And the idea is this: if there's little variability within one sample compared to a lot of variability between samples, then that would insinuate that the data is not very mixed up, and so the data would be nicely separated into distinct groups. And then that gives you a pretty good indication that the samples have different means, because all the data is nicely separated out into groups instead of the data being all mixed in together. So that's what I'll say about that, right? In a nutshell and kind of conceptually, that's why we're analyzing variances. We're comparing the within sample variances to the between sample variances. If the within sample variance is small compared to the between sample variances, then that means the within sample, or that means that the individual samples are all separate. They're all separated out, and so they're going to have distinct means. The ANOVA test is a really good test. It's pretty powerful, and it's a pain in the butt to compute by hand. Okay. The test statistic follows an F distribution. Okay. F is the between sample variability divided by the within sample variability. Or in other words, the mean square is due to treatment divided by the mean square due to error. These two things, so mean square due to treatment is given by this thing, mean square due to error is given by this thing. They're nasty. It's just nasty. That's all you really need to know is that it's nasty. But you get that test statistic. You compare it to the, or you use it to compute the p-value. And again, same interpretation of the p-value as always. If the p-value is small, right, the p-value is the probability that we would get the test statistics that we got if we assume that the null hypothesis is true. So if you get a small p-value, then that casts doubt on your assumption, right? And so you reject it. You reject the null hypothesis. Okay, so without further ado, take a look at an example. Oh, well, let me say one more thing before we do. There are conditions you have to check, as usual. And the conditions you have to check to run an ANOVA are these things, right? So these samples have to be independent, they have to be random samples, they have to come from populations that are normally distributed, so you check normal probability plots to make sure of that. And then the fourth condition is that the populations have to have the same variance, which is a difficult thing to test for because you probably don't know what the population variance is if you don't know what the population mean is, right? So in practice, we assume that condition 4 is met as long as the largest sample standard deviation is no more than twice the smallest sample standard deviation. I'm never going to ask you to check conditions, okay? But just in practice, in the real world, these are conditions that you would check before you run the test. To actually run the test in StatCrunch is really simple. You go to Stat ANOVA, one way, and that's it. So let's look at an example. It says the data below show the shear bond strength for different repair kits for chipped porcelain measured in megapascals. A sample of 20 porcelain specimens was taken and the bond strength measured. Determine if there is a difference in the mean shear bond strength among the 4 treatment groups at the 0.05 level of significance. Okay, so it was a sample of 20 porcelain specimens, but it looks like they did 5 for each different kind of repair kit. So each repair kit has a sample size of 5, I suppose you could say. I'm going to call Kojak Group 1, Sillistor Group 2, Samara, or however you say that, Group 3, and Ceramic Repair Group 4. Let's see if there's a difference in the bond strength of these different kits. So the null hypothesis is that there's not a difference, right? That the mean bond strength is the same for all 4 kits. The alternative is that at least one mean is different from the others. Okay, and to run the test, we go Stat ANOVA, one way. Okay, let's do it. We're also, of course, going to have to get that data into StatCrunch. So here we go. Okay, my kids are watching a movie, so if you hear stuff in the background, that's what's going on. Okay, let's run the test. So I've got the data in. Let me make sure it's in there correctly, actually, real quick. Those look good. That looks good. Looks good. Okay. All right. So to run the test, we go stat ANOVA, one way. We want to compare all 4 of these columns. So I'm selecting all 4 of them. And then that's it. I'm just going to go ahead and hit compute. And we get all kinds of good stuff here. We get our test statistic. I'm not sure which one of these is the MST and which one is the MSE. Maybe, oh, I think they're down here. I think mean squared due to error for sure. Mean squared due to treatment, I don't know. Maybe this one, I'm guessing. I'm not exactly sure, to be honest with you. It doesn't really matter. The p-value is right here, and that's what we want. We want the p-value. It's also nice they give us the sample mean and sample standard deviation for each of the groups up here. So that's really useful information actually, because just looking at these sample means, it's like, to me, it seems like Cojet and Sillistor have a pretty similar sample mean, and it seems like Samara and Ceramic Repair have a similar sample mean, but it seems like those 2 groups, Cojet, Sillistor, Samara, Ceramic Repair, have different means from each other. You know what I mean? And certainly the p-value is indicating that there is a difference, right? It's telling us your p-value is really small, so you're going to reject the null hypothesis, right? So let's write that down. Our p-value is 0.0023. Okay, since 0.0023 is less than 0.05, we reject the null hypothesis. So, at the 0.05 level of significance, the evidence suggests that at least one repair kit has a different mean bond strength than the others. Okay? And that's it. In 13.2, we're going to talk a little bit more about doing some further analysis on this to figure out exactly which means are different. But even just looking at the sample means that we saw in the ANOVA table in StatCrunch, it's pretty clear that these first 2 are the same, these last 2 are the same, but the 2 groups are different from each other, right? Pretty clear that that's what's happening. But that's that one. Okay, let's look at one more example, and that'll be it for this particular section. It says, an obstetrician knew that there were more live births during the week than on the weekends. She wanted to determine whether the mean number of births was the same for each of the 5 days of the week. She randomly selected 8 dates for each of the 5 days of the week and obtained the following data. Test the hypothesis of equal means at the 0.01 level of significance. You don't have to check conditions. Good, because I wasn't going to anyway. Okay, here we go. So I'm going to call these things groups 1, 2, 3, 4, and 5. The null hypothesis is that the mean for each of those days is the same. Mean number of live births, right? Doesn't mean they're streaming it online or something. That just means the baby was born alive. It's kind of sad to think of the alternative, but anyway, that's the null hypothesis. And then the alternative hypothesis is that at least one mean is different from the others. Okay, so just looking at the data, in other words, like reading the scenario again, it's like, it's a known fact that there are more live births during the week than on the weekends. People don't want to ruin their weekend by having a baby, I'm just kidding. That was a joke, a bad joke. That was a joke. No, no. But there are more live births during the week than on the weekends. And you might think, well, how is that possible? But I think the reason for that is because a lot of live births these days are C-sections, right? Cesarean sections, and so, or like you go in and you know. You're induced, right? Labor is induced to get the baby coming. And so the obstetricians have some control then over when the birth takes place, if they're going to schedule a C-section or something like that. And since probably a lot of obstetricians don't want to come in on a Saturday or a Sunday, it makes sense that there are going to be more live births during the weekdays. Now, the question that this particular obstetrician has is, does the number of live births differ during the actual days of the week? And looking at this data, I would guess yes, because if you look at Monday, the number of live births on Monday seems about, on average, it seems about 1,000 smaller than the other 4 days of the week. So I'm going to guess that we're going to reject the null hypothesis again because of Monday. So apparently obstetricians don't like Mondays very well. So they don't schedule live births for the weekend, but they also don't schedule births for Mondays. Anyway, but we'll see. We'll run the test. Stat ANOVA one way. Okay, let's go to StatCrunch and get that data into StatCrunch. Whoop. Uh-oh. Did something weird. Monday, Tuesday, Wednesday, Thursday, and Friday. Okay, let's see. Okay. Oh, goodness gracious. All right. 11, 6, 2. Uh-oh, this one is definitely wrong. What was it supposed to be? 12, 0, 2, 3? 0, 2, 3. Okay. Bear with me, I'm almost there. Okay, now let me make sure I got those in correctly. Just do a quick once over. What a pain to enter in these big 5-digit numbers, man. And so many of them, too. It's looking good, though. So far, so good. Thursday. Okay, Friday. Okay, it all looks good except for that last 0, which doesn't need to be there. Okay, let's run the test now. Stat ANOVA one way. Oh, I want to compare the days of the week now, right? So I want Monday through Friday to be compared. And I'll hit compute. Oh yeah, look at that p-value. We're definitely rejecting the null. Let's look at the sample means. So the sample means, oh, well, there is a more difference than I expected, but definitely Monday's smaller than the others, right? So Monday's smaller, and then Wednesday, Thursday, Friday, and Tuesday. Tuesday's the most popular day. But you notice there's like a difference of 200 between Tuesday and Friday, and a difference of a difference of like 200 between Thursday and Friday, and a difference of maybe 300 between Wednesday and Thursday. But then there's a difference of like 500. No. What numbers am I looking at? 15? So like 1,000. There's a difference of like 1,000 between Wednesday and Monday. So, so yeah, big difference from Monday to the rest of the week. What rest of the days of the week? Anyway, we're rejecting the null. Let's write it down. So our p-value is less than 0.0001. Consequently, we're going to reject the null hypothesis. All right, our level of significance this time was 0.01. So we reject the null. So at the 0.01 level of significance, the evidence suggests that the number of live births is not the same for each of the 5 days of the week. Okay, so the evidence suggests that the number of live births is not the same for each of the 5 days of the week. And that'll do it for that section. Okay, so here's your assignment, and you can skip any parts that ask you to check conditions, right? So don't worry about checking conditions so much. So that's that one.